Okay, welcome to lesson 7, and the topic today is combinations. And you have seen combinations already. I said we're going to dedicate an entire lesson to it, and that's what we're doing right now. So I can explain and apply combinations to real-world applications. So before you were just seeing the connection, here's a combination, here's Pascal's triangle, how do they relate? Now we're going to look at them more specifically. So review of permutations, order mattered so importantly. And your notation for that, again, was NPR, which could also be written as permutation of NR, and the formula for that is N minus R factorial. But the big thing for me is that order matters. Okay, very, very important. Combinations. What makes a combination different from a permutation? It really comes down to order does not matter. Order does not matter. So you can see why I was emphasizing before when order mattered when we were doing permutations. For combination, order does not matter. Okay? Just a review for combination notation. There are 3 of them. Pick the one that you like best. I'm going to try to use all 3 just to be create a little bit of flexibility. The first example, I'm going to explain why combinations are the way they are. So how many ways can 3 seats be filled from a selection of 5 people? Where order does not matter. So I'm not going to, that's in that question for us right there. So what happens is, what we're looking at is we have 5 individuals, okay, and we have 3 seats. So maybe I'll start off with using diagrams here. Okay, here are my 3 seats. For the first selection, I have 5 people available. For the second one, I have 4. And for the next one, I have 3. So right now, it's a permutation. All right. The 3 people that get picked, though, the 3 people that get picked are considered people. All right, and all people are equal. Okay, and if that's the case, that means that they are also known as clones. Okay, so that means we have clones here. So that would mean that, finishing off the math, we'd have 5 times 4 times 3 divided by, if each of those people are a clone, I would have to divide by 3 factorial. Okay, which would mean, when you calculate that out, the 5 times 4 times 3 gives us 60 divided by 3 factorial is 6, so it gives us 10. Okay, and this is the key right here. When order doesn't matter, the people being selected or the objects being selected are clones. Now, if we take a step back, so I'm just showing you where it comes back, or where it all ties together. So the top, that was a permutation. So we did the permutation of 5, and we're going to pick 3. And then we divided by the number of clones, which was, it's always the amount you're going to pick. So it's 3 factorial. So really, this is simply n factorial over the 3 factorial on the bottom is r factorial, and that's the n minus r. So this part here is from the permutation. The r factorial matches up with the clones, or what we're trying to get rid of. So therefore, the answer here is simply put, 5 people, 3 is going to equal 10. All right, so it's just a combination. So combinations, order does not matter. Can't stress that enough. Okay, order does not matter for a combination. Okay, so obviously went through, tried to explain everything there to you. All the examples aren't going to look like that. So let's run this in kind of real time. So a job requires a plumbing company to send a team to fix a problem. The company has 4 experienced plumbers and 4 trainees. If a team consists of 3 plumbers, determine how many teams exist if each team needs to have 1 experienced plumber and 2 trainees. Okay? So, complicated question. I'm kind of jumping into sort of your upper end combination question, but the order doesn't matter. It doesn't matter what plumber is selected, but the bottom line here is I'm going to go with experienced and trainees. All right, and I'm going to use the combination, the stacked combination notation here. Okay, so I have 4 experienced plumbers available. I have to send 1 to do this job. Okay, so that means there's my 1. It's going to happen at the same time, so it is multiplication. I have 4 trainees, and I'm going to send 2 with that experienced plumber. Okay, so it's a rule of product here. So it's my experienced plumbers multiplied by my trainee plumbers. This would be the same notation as 4 combination 1 times 4 combination 2. The reason I like the stacked notation is because the bottom numbers they have to add, must add to the total required. I'm going to send 3 people, so it's a quick check for me. So I know that the bottom ones better add up to 3 to make sure I have enough people. Once you have that figured out, that's the tough part. Now it's just calculator. You're just doing combinations here. So you can do 4 combination 1, or the combination of 4 choose 1, I should say, is the correct notation. So 4 combination 1 multiplied by 4 combination 2, we get up with 24. So therefore, 24 plumber teams could be created. Could be created. So these are your upper end questions actually when it comes to the combinations, when you're looking at different ways to arrange particular teams. So the next example, there's 5 boys and 7 girls in a room. Determine how many 2 boys and 3 girls must be selected. Determine how many 2 boys and move to another word. Oh, I'm missing the word way. Determine how many ways. Let's get rid of the many here. Determine how many ways 2 boys and 3 girls could be selected. Man, that's just poor grammar altogether. To move to another room. Okay. So you're looking at your boys and your girls. I'm going to use this, I'll use a different form this time. So order does not matter. How do I know order doesn't matter? I'm picking a group. Okay. So I'll put this over here as a hint. If picking a group, order does not matter. Doesn't matter. All right. So if we're picking a group of people to go do something, as soon as you use that word group, order doesn't matter. Okay. So how many boys do I have available? I have 5 of them. How many do I want to move to the next room? Well, I got to pick 2 of them. A boy's a boy. 2. It doesn't matter which one, so order doesn't matter. For the girls, there are 7 available. And I want to pick 3. And girls, not necessarily girl. Each one's unique and important and smart, so not like the boys there. But anyway, that's the setup there. You have your total number available, and you're only picking a couple of them, and you do that multiplication to determine the final number of possible groups that could be chosen. So we find that there are 350 different groupings that could be created. Different groupings. So remember, you're going to have less combinations. When order is not important, there'll be less resulting groupings because we don't consider any of the combinations unique, which therefore cuts down on how many would be available for that. All right, and last example here. There are 5 married couples at a party. Determine how many ways a man and a woman could be selected to play chess, because that's what we all do when we're married, apparently, if they cannot be married. So they can't be a couple. If, put a they in there, cannot be married. No couples. No couples. So the order doesn't matter. It doesn't matter which person's chosen. All right. But we have 5 married couples at the party. So we basically have a man and a woman. So it's going to be a cross-gender chess game. So let's look at the men. Okay. How many men are available? Well, we have 5 men available. We want to pick one of them to play chess. Now for the women, how many are available? Well, depending on what male is selected, we don't actually have 5 women to pick from. We only have 4 women to pick from because we got to throw the married one out. Got to get rid of the wife. Oops, I didn't say that out loud. I meant we must ignore the. No, we're not going to ignore it. We're not going to choose the wife that the woman that's matched up with the man. So it's going to be 4 choose 1. So that will get us the number of ways that we can select a non-married couple to play chess. Now when you calculate that out, you get 20. So therefore, 20 ways to create partners for chess. Tell me that doesn't sound like a lot of your Saturday nights. Come on, you can admit it. You go party, play some chess. B part, determine how many ways 2 men and 2 women can be selected if none of them can be married. Okay? How many ways can 2 men and 2 women be selected if none of them can be married? And what we're going to find, we're going to approach it the same way. And it doesn't matter whether you start with the men and the women. But the men, if I have 5 to choose from, I'm going to pick 2 of them. And because order is not important, we can actually do this selection, and then we can say to the women, okay, the ones that are married, go off to the side there. So now there's only 3 women left to choose from in order to pick the remaining 2. Okay? So you just eliminate them as you go through and do your calculation. So now you just got to punch that into the calculator. And we come up with a total of 30. So therefore, there are 30 different groupings. All right, so the homework's going to focus on combinations. You're not dealing with mixing them up yet. You want to just focus on doing these types of questions that we finished with and working on actually entering them into the calculator properly. So that's what the homework will focus on. If you have any problems, please let me know.